Hello. So today we'll be talking about Concurrency Kit and Multicore synchronization. So Concurrency Kit was a library that was recently introduced into the FreeBSD kernel, and it aims at providing concurrency primitives for high-performance concurrent applications. So what we'll be doing is actually going through a tour of various advancements in concurrent parallel algorithms over the last 30 years or so, 27 years. And this is sort of the breakdown. So we'll start off just covering a little bit of background with respect to multi-core synchronizations, multi-core systems, et cetera. And then we'll deep dive into concurrency primitives, so understanding what features are supported by underlying hardware for building concurrent algorithms and parallel algorithms. Blocking synchronization primitives, so things like read-write locks, mutexes, et cetera. Asymmetric synchronization, and then last but not least, we'll touch on non-blocking synchronization, so lockless algorithms, LockFree algorithms, and their applications. And if there are any questions at any point in time, just feel free to interrupt. All right, so bit of background. It is a fairly dense talk, so there isn't much background. So concurrency ultimately was developed for performance. It is rooted in, its roots are in operating system design and implementation, and it provides performance either via latency hiding or throughput. And these days it is ubiquitous. Even on a single processor, typically multiple is ubiquitous, and by ubiquitous, I mean even in the context of a single processor, you do have instruction level parallelism. And these days, with the ubiquity of multicore, the problem of designing applications that efficiently utilize all these cores is even more difficult. You have issues around NUMA and asymmetric access to memory. So for example, if this core wanted to access core memory that is available to this core, so this is on a single die. You know, if there's some cache currency traffic, if they're interacting with shared data, they would have to go via an interconnect and the unbus, and there's a latency hit due to that. Also, when it comes to multi-core algorithms, typically efficient concurrent algorithms will end up being implemented using hardware, relying on hardware support for these primitives, such as atomic instructions, fences, et cetera, et cetera. In addition to that, you have concerns around memory coherency, so you have to be careful how you're sharing state between processes. And now all of a sudden you have problems around memory models, which are more relaxed. And then last but not least, overall program complexity is also increased. I think multi-threaded applications have a reputation of being very difficult to design and implement correctly. So now when you bring multiple cores into the picture, this becomes an even bigger problem. So a lot of research has been put into this, and despite major advances over the last 3 decades, most software today does not take advantage of any of these advancements. And especially, I would have to say, the BSD family of operating systems. This includes improved data structures, improved synchronization algorithms, hardware support, things like Intel's support for restricted transactional memory, TSX, as well as the power architecture. So historically, the reason you haven't seen this is either A, the languages lacked the primitives to be able to implement these algorithms efficiently, or reference implementations were available only in the literature, and they were either incorrect or they just really sucked and were not practical for real-world use. So overhead was extremely high, or they weren't fit for unmanaged languages like C or C++. So particularly in the realm of high-performance concurrent algorithms, a lot of those tend to be designed with languages like Java in mind, which obviously isn't very relevant for the types of workloads involving C, C++, et cetera. So this is what ultimately gave birth to Concurrency Kit. It is BSD licensed. It supports freestanding environments. So the idea is it should work in pretty much any kernel. Different kernels should be able to plug in different shims to implement things like blocking, et cetera. So it supports freestanding environments. It's part of FreeBSD. It supports a Linux kernel. It's heavily used in user space as well. And it's been actually used in a couple of research kernels out there as well. And the idea is let's have one library with high-quality implementations of these algorithms and data structures and so forth, and collaborate in building these algorithms rather than fragment the engineering resources across different communities. There is a lot of overlap here. You have n different projects implementing the same exact data structure, and usually they're all broken in various different ways. So that was sort of what motivated Concurrency Kit. And it aimed to also solve some of the problems up here. So the first problem was really concurrency primitives, so atomic operations. So back when Concurrency Kit was first implemented, standard atomic was just not available. And due to that, we ended up implementing a very rich family of concurrency primitives within Concurrency Kit. So even though standard atomic is pretty much ubiquitous today, unfortunately, there are still cases where you do have to rely on inline assembly. So to touch on this, here's a simple example. So Intel provides the richest set of atomic operations available on any architecture today. However, several of these operations are still not implemented in their native form in standard atomic and various libraries that are available out there. So very simple. One example is BitTestSet. So in this code, we just want to set the second bit on a value atomically, and then the program or this function will return 0 if that bit was set. Very simple code. So if we were to use something like standard atomic, you end up having to implement this using compare and exchange, and it's fairly heavyweight. Obviously, if you do have a first-class implementation of that, code ends up being a lot more efficient, a lot simpler, et cetera. So there are all sorts of instructions, at least on x86, which don't have a one-to-one mapping in standard atomic. And unfortunately, optimization around atomics is also in its very early stages. So for example, a very common operation, particularly around reference counting, is to do an increment with 0 flag, or more specifically, decrement with 0 flag. And there is no way to really implement this if you're using standard atomic, using the actual underlying instruction that's available. Another important piece of functionality, which sort of state-of-the-art doesn't really provide an abstraction for, is load-linked stored conditional. So this is provided on ARM, Power, and several other architectures. It's a lot better than CAS for sophisticated concurrent algorithms, lock-free data structures, et cetera. But unfortunately, it cannot be directly utilized in C. And this is an example of something where existing high-level abstractions don't work, and you unfortunately do have to rely on things like inline assembly, unless you're implementing a compare and swap operation on top of LLSC. Another thing that is missing in standard atomic, and at least the Rust language is looking to close the gap here, is CPU relax or CPU sleep. So on x86, if you're doing any kind of semaphore spin weight, it's recommended that you utilize a pause instruction, which it's kind of ambiguous what it does today, but they recommend it's used in any of these spin loops. The idea is it utilizes significantly less power and pipeline resources when you are within these spin loops. Back in the Pentium days, this was essentially a cheap load barrier. Today, it's not documented what exactly it does, other than the fact that it's recommended. Power, on the other hand, has something a lot more sophisticated. You could actually change the priority of the hardware threads at runtime. You can essentially yield at the hardware thread level. So this is another example of something that is not exposed in languages today. It is available in Concurrency Kit. Other interesting piece is recently Intel released support for prefetch instruction that allows for read for ownership. So a very common pattern that you'll see in concurrent code, particularly with something like compare and swap, is you may load some value of memory from a cache line and then a couple of cycles later execute a compare and swap. And this actually requires more cache currency traffic than necessary. So you end up having to read something, transitioning the state machine and all the cache currency protocol state machine to another state and all threads, and then when you write to it, you end up with an eviction. So you end up having to do 2 broadcasts on a multi-core system. So there is the ability to actually read this data and validate. So it's just 1 cache currency cycle. So this is also something that is included in the Concurrency Kit primitives. Another really cool thing that's been introduced is transactional memory support, so restricted transactional memory, so there's no guarantee that your transaction is ever going to complete, but most of the time it does work. A very common use case for this is lock lesion, and this is something that is available in the glibc library today. So over here we have a very simple program, consists of 2 threads. Thread 0 locks this global lock called lock, and then it writes a value into the first element of an array, unlocks, and then thread 1 also issues a lock, writes a value. In this case, it's on a separate cache line and unlocks. So if you're using a traditional lock, this ends up being serialized. So lock lesion allows you to elide the lock, assuming that there are no conflicting memory accesses within that critical section. And by conflicting, I mean overlapping reads or writes to regions of memory. So now this critical section can execute in parallel. So this is very cool for sparse data structures where there is, how can I say? It is likely that there will not be conflicting memory accesses. So something like a hash table would be a great fit. But if you're using a splay tree, which you probably shouldn't be using in 2017 anyways, it would not be a great fit because you end up modifying a lot of memory. So in Concurrency Kit, there's an abstraction called CK Elide, which is plug and play. So you can plug in any lock implementation, and it'll implement the correct semantics for lock lesion, and it has some adaptivity as to when it elides, when it aborts, etc. So it tries to be intelligent about when restricted transactional memory should be used. Cool. All right, so kind of touched on sort of various concurrency primitives available to Concurrency Kit today, which are not really fulfilled by existing standards. And now we will touch on traditional synchronization primitives such as mutexes, etc. Cool. Was there anything in the concurrency primitives you guys or you all wanted me to touch on or revisit? Questions? Cool. All right. So most of the lock implementations you see out there in the wild tend to be centralized, greedy locks. So you'll have one region of memory, which represents the lock, and all threads essentially contend to acquire the lock by performing mutations to that region of memory. And there are a couple of problems with that, which we'll touch on in this section. One is it's not fair, it's greedy. There's no guarantee of starvation freedom, which is particularly important for NUMA. We'll get into that. And obviously, it's not scalable because that lock is in one region of memory, right? So there's actually a myriad of locking implementations out there, So over here you have struct mutex, and then all the CK prefix locks are locks provided by Concurrency Kit, which provide different guarantees as far as fairness, scalability, fast path, and space utilization. I'm not going to go through these one by one, but if you do grab this deck later, the A means the number of atomics on the fast path, and F means the number of fences. Fair means you have guarantees of starvation freedom. It's not essentially FIFO fairness, just starvation freedom, and scalability. So as you increase the number of cores, you don't end up degrading system performance, which, again, we will revisit. So starvation and fairness become especially important on NUMA, and NUMA is pretty much ubiquitous today. Even on a single socket, you do have NUMA effects. This was a benchmark I ran a while ago on an 8-socket Linux machine. And on Linux, you have VDSO and get time of days essentially implemented in this shared page. That shared page tends to be on the first core, on the first socket of a machine. And this was timing of get time of day of a process pinned to different cores on the machine. This is an 8-socket machine. And that particular topology, depending on the core you were on, you could be up to 2 hops away from the VDSO page. And you'll see an almost 20% performance difference in get time of day depending on the core that you were on. You'll also see this sort of thing with locks. So something that was done in Linux a while ago, a few things. One is adoption of a fair centralized lock called the ticket lock, particularly to address issues around NUMA. Over here we have a simple compare and swap based lock running on 2 different cores, and this is the number of successful acquisitions in this particular benchmark. And you can see there is a good amount of starvation, right? So the second thread, which is bound to the second core, was able to acquire this lock much higher, and that happened to be because it was on that core's memory. And you can actually see this at a much lower granularity as well, and Intel did some work to also improve the fairness of compare and swap, at least when you are inter-socket. To the right here, we have a fair and scalable lock. It's fair in the sense that in this particular case, you have FIFO fairness. Threads are guaranteed if they issue a lock acquisition request, they will be able to acquire the lock eventually in order. And then the other piece is that it's scalable. So in this particular situation, the memory for that lock is distributed. And it may sound like a misnomer to have a scalable lock, but this is what a typical naive lock would look like. So the red line here is a centralized greedy lock. It is has no consideration for NUMA. And you could see that under load, performance actually degrades. And this is due to all the cache currency traffic, and that ends up degrading overall system performance. So a scalable lock should at the very least saturate and then sustain that peak throughput. What this graph represents is it's a file system benchmark. This is run on Linux. And there's a global files lock there. And they found that essentially system performance just benchmark performance slowed down to a crawl. And what they did recently there is they introduced the MCS lock, which is part of Concurrency Kit as well. And they were able to achieve this significant performance improvement. Now, fairness is not free. So if you have a good amount of jitter on your system, there is a significant impact on system-wide throughput. So you'll see over here that the overall number of transactions in this greedy lock implementation is significantly higher than the MCS lock. And that's, in this particular case, they're running in user space, and I did everything I could to minimize jitter within reason, and there was still jitter, and this led to this significant reduction in system-wide throughput. So that's it on locks. I do encourage, looking at the various implementations out there. There are always new algorithms being developed. There's one that was just published a few months ago, which was a NUMA-aware, even more NUMA-aware MCS lock. And that's the sort of thing that will also get lifted into Concurrency Kit. So asymmetric synchronization. First thing we're going to focus on is read-write locks. So you have a similar graph here. It tells you the bias, write bias versus read bias versus none, fairness, scalability, the fast path for the reader. So here I'm assuming it's particularly of interest for read-mostly workloads, and then the space requirements. So there are asymmetric synchronization primitives out there that do provide scalability and practically, how can I say, an extremely low contention fast path for readers. And then you have implementations out there that provide better biasing. And I think that's of particular interest. You do see a lot of work around fairness and adoption around fairness for mutexes, but there aren't that many production systems that have looked to improve the read-write lock implementations to prove biases between readers and writers. And of particular note is phase-fair and task-fair lock, which we'll revisit shortly. So I was mentioning scalable read-write lock. So the big reader lock has been around forever, and what that does, it's a distributed naive read-write lock, and it does require that every reader have essentially a local, how can I say, a record registered that's associated with the lock that it ends up spinning on. And whenever a reader attempts to acquire a read side critical section, it mutates its local node. So it's not stopping on global memory ever, and the only interaction with the write node is a read. So it ends up being very, very fast for readers, but it does come at a cost for writers, because now when writers attempt to acquire the lock, it has to scan all the nodes across readers to determine that the lock is available. So for subsystem locks, I would highly recommend big reader locks, but obviously if you have something hanging off, something that's a lot finer grained, it's not the best fit. What this graph presents is a read mostly workload, where we're essentially acquiring a reference from an array in a loop, and we're doing a whole bunch of reference counting around that. What you'll note here is the traditional read-write lock and read-write lock with reference counting simply does not scale, and you'll see that the big reader lock performs very, very well in this scenario. The reason for that is the centralized locks, even though they are read mostly, end up becoming write heavy because you are mutating that reference count continuously or mutating the lock continuously, so you end up having a lot of cache line bouncing. And then there's this concurrently readable workload, which we'll touch on in a bit. So I mentioned biasing early. I find this to be very interesting. So most read-write lock implementations out there are write bias in the sense that if you have a concurrent lock acquisition attempt from a reader and a writer, or you have readers queued behind a writer, the writer is always preferred over the reader. So there are execution histories where you will end up starving readers, or you'll end up in this situation where you're essentially live lock, particularly if you have very long read-side critical sections. Now there are task-fair locks that are available out there that ensure that read-write locks are acquisition attempts are resolved in request order, and then you have phase-fair locks, which makes assurances by guaranteeing how can I say, fairness around read and write phases, right? So if a write was the current acquirer, it's guaranteed that if there are any pending readers, they are handed off the lock upon unlock. And once readers unlock, if there are pending writers that come in prior to any potential readers, that writer is guaranteed to be handed off. So this can have a lot of interesting implications on quality of service, and it's plug and play. You could just replace the read-write lock that you have today, and you may end up having amazing performance improvements. This was, a while ago I was working on a firm real-time system for online advertising. Timescales were on the order of 100 milliseconds or so. We had massive read-side critical sections because we're just lazy, frankly. And just simply replacing the lock implementation with a phase-fair lock gave us a significant performance improvement. Another very interesting primitive is a SetLock or a sequence lock. This is extremely write biased. There's no forward progress guarantee for a reader. But the nice thing is if your update rate is fairly low, it's extremely efficient. For the readers, excuse me, on TSO architectures, there are no atomics or memory fences on the fast path. And for writers, depending on how you implement the sequence lock, that can also be the case. So that's provided under this primitive. All right. So one big problem with any of these asymmetric workloads is how can you ensure reader progress? How can you ensure if you have readers and writers that readers are still provided assurances around forward progress? And for any of these for any of these workloads involving blocking synchronization, as soon as writers are introduced, readers degrade significantly. And this is a very common problem, particularly around workloads where you decouple liveness and reachability of an object. So anything where you end up using reference counting. So not only is reference counting expensive, but the blocking aspect of that synchronization just completely destroys read-side performance. So this is where techniques like RCU in the Linux kernel were adopted. And they've been, obviously, RCU is pretty ubiquitous in the Linux kernel, and you have a user-space RCU implementation as well. So how RCU and all these various memory reclamation mechanisms work is they provide the same safety guarantees as reference counting, but the difference is they have minimal to no interference to readers. Depending on the algorithm that they're using, some are better suited for read mostly workloads, such as RCU, and some are better suited for write mostly workloads. So what you have here is a read mostly workload, and you'll note that the big reader lock scales well. If you introduce any writers, again, you end up with terrible performance. All of a sudden, any guarantees you had around latencies are destroyed. So a very simple alternative to reference counting is hazard pointers. So the way hazard pointers work, it's very similar to a garbage collector. Whenever a reader acquires a hazardous reference to memory, it will essentially push that to, for the sake of simplifying a little bit, it pushes it to a global list to publish that it has acquired that reference. And then, unfortunately, this is where there is an impact on the fast path. You do have to issue a full memory fence. The reader then checks that the data structure, the data member acquired the reference to has not changed, and if it hasn't, then it is safe to access that region of memory. And the way deletion works, it's similar to reference counting. So you do a logical delete. This is what happens here. So we will, in this case, we're acquiring a reference to an array on the reader. On the right side, we acquire the reference, make sure that it's logically deleted, so no additional references can be made. We issue a full fence, and then what you do is actually amortize the cost of destruction. So rather than just synchronously destroying it, you put it on some list. And then once in a while, you prune that list, and you walk through this global list of pointers that readers have pushed on. Again, you do have to use a fence. You do actually have to use a fence prior to reclaim as well. If any pointer on the free list, on this deferral list, is not present in this global list of references that readers have acquired, then it's safe to destroy. So the nice thing about this is, the ReadSide stuff could actually be implemented using, per CPU structures or thread local structures. So it does scale a lot better than reference counting, but there is a cost to the fast path. The other nice thing about this is for more advanced data structures, like LockFree data structures, you can actually use this, while reference counting is not a good fit. This is another algorithm that's also available in Concurrency Kit. So the downside to hazard pointers, the other downside besides the memory fence, is you do require memory to be allocated for all ReadSide references. So for example, if you're traversing a list, you may require up to 2 nodes. If you're traversing a tree, you may require up to log n slots in order to ensure that those hazardous references are safe. So alternatives do exist, and RCU is a very common one. There is a lot of FUD around that. There are actually alternatives to it. One of those is in Concurrency Kit. It's called Epoch Reclamation, which was developed many years ago by Kira Fraser in the context of garbage collection. And that can be used to implement similar things, similar guarantees as RCU. And in fact, the Concurrency Kit CK Epoch implementation, which I won't deep dive into here, is faster than the URCU implementation that's out there, and it does support sleeping, etc. So the downside to these passive schemes, though, is they do block writers. So they're not good for write-heavy workloads. Writers essentially have to wait for readers to make a certain amount of forward progress before they can reclaim memory. So, and central to this is this notion of grace period detection. This is why it becomes a problem. So for example, you have 3 threads here. Thread 0 is a writer. Thread 1 and 2 are readers. Thread 0 does a logical deletion at this point in time. Thread 1 and thread 2 issue a read for some particular data structure. The writer issues a synchronized operation, which essentially blocks until all active reads are completed. And then after all active reads are completed, it's guaranteed that the logical delete is globally visible, so no one can acquire a reference to what was just logically deleted, and physical deletion can occur. Now, the hard part to implementing schemes like this is how synchronize is actually implemented. And this is what an API using a passive scheme would generally look like. So on the read side, you have something that looks like a ReadSide critical section, like a read lock. This is what the reader does. So it essentially marks a region of code as having hazardous references. It acquires references to whatever number of objects, does stuff with them, and then ends a critical section. Now the cool thing here, unlike reference counting, is whenever you acquire these references, there is no cost on the fast path. We're not incrementing reference counters or anything like this. If you're traversing a tree or accessing a million nodes, you're paying the cost of a single ReadSide critical section, which depending on the implementation may also just be a no-op. And then on the right side, this is an example. Let's say the right side is just randomly deleting nodes from this index. What it would do here is issue a logical delete using, by, in this case, setting some index to null, and then blocking on synchronize. Once all readers which may have potentially started prior to this, the completion of put and it being visible to all threads, it will actually be able to destroy objects. It'll block until all concurrent readers with respect to that current synchronized call. What does this look like? So here's a very simple implementation, just using timestamps. So what we're doing in this case is in SMR begin, we're just doing a compiler barrier. It's a no-op. And then on end, also compare your barrier. And then every n ends, so let's say every 100 ends, what we do is just grab the current time, issue a memory fence, and reset our counter. And what synchronize would do is grab the current time, issue a memory fence, and then wait until all threads have observed the current time. And in that way, you have assurances that if a logical delete was to occur prior to the synchronized operation, it would, how can I say? Prior to the synchronized operation, by the time that the timestamp is globally visible, because this timestamp is ordered with respect to, how can I say, with respect to all threads, there's an inherent global ordering to its time, then any hazardous references, anything that is pending destruction now has been logically deleted is safe for destruction. And there's actually, again, a whole bunch of implementations. So the mechanism that RCU uses is called quiescent state-based reclamation, and there's some recent work done around sleepable RCU to be able to handle interrupts and blocking in kernel space. But you also have hazard pointers, and then in Concurrency Kit you have epoch-based reclamation and a variant of epoch reclamation as well. And this is a breakdown of the fast path for the same benchmark we showed earlier. And this is a read mostly workload. All right, so last couple of things I wanted to touch on is non-blocking synchronization. So non-blocking synchronization is a term of art. It provides very specific progress guarantees for concurrent data structures, and it provides a high amount of resilience. So you get things like reentrancy. You don't have to worry about deadlocks. Depending on the data structure, you may not have to worry about starvation, etc. So the two primary non-blocking guarantees that you get today are lock freedom. So that provides system-wide progress guarantees, meaning if one thread is always guaranteed to have to be making forward progress. So for example, if you have a stack data structure, the only reason a thread would be delayed is if some other thread was making progress. So overall system throughput is sustained. And then wait freedom provides per operation guarantees. So every wait-free operation is guaranteed to complete in a finite number of steps for every thread. So this is a hierarchy. Lockless algorithms are not technically non-blocking. You don't have these guarantees. Typically, they do have blocking on fast path. So buffering and NP-ring and the FreeBSD kernel are examples of that. They are blocking. You don't get the same level of resilience as a true non-blocking implementation. There is a lot of hype around lock-free data structures. The key thing, a very important thing to note is lock-free data structures and wait-free data structures can provide very strong guarantees around latency. They're not necessarily good for the fast path, especially if it's generalized to any number of readers and any number of writers. The impact on the fast path really depends on the underlying instruction set and the algorithm that you're implementing. So here's an example of the fast path of a lock-free stack compared to a stack protected by a spin lock on x86 versus power. And on x86, a stack that's protected by a spin lock ends up being significantly faster. We use much cheaper atomic operations on the fast path, and it's just one atomic operation on the fast path. On the other hand, on power, that isn't the case. The lock ends up being significantly more expensive. So an x86, push, pop, etc. are implemented using a compare and swap operation, while the lock could be implemented using something significantly simpler. So when do you start seeing benefits in these algorithms? It's typically under contention. So once you hit a certain amount of contention, then you will get better performance effects with respect to the exhibited latency distribution. So here is an example latency distribution of a lock-free stack compared to the spin lock protected stack. So this is a spin lock protected stack's latency distribution, and this is a lock-free stack. Now what you really can't see here is the fast path is actually slower for the block-free stack. But once contention is introduced, it is significantly faster. The upper bound, it's a lot more bounded. There was some interesting work done here recently that also showed that could be argued that lock freedom is practically weight-free for most user space applications. Now the downside, one thing to note is lock-free data structures that do dynamic memory allocation, use malloc-free, etc., do require runtime components such as RCU or epoch reclamation, etc. However, you have a lot of structures that are bounded, don't require memory allocation, that provide you these forward progress guarantees. For write-heavy workload, what this means is these dynamic structures end up not being a good fit for write-heavy workloads because runtime component, so RCU, EBR, do not perform well under those workloads. So in the real world, a very nice thing to do is actually specialize your workloads. So rather than developing for any number of readers and writers, bound it to a single reader, single writer, or mini reader, single writer, etc. So Concurrency Kit does provide various mechanisms for that. So one thing is ring buffer, which is pretty much a plug-and-play replacement for buffering. And with a few extensions which are coming up, would also be a good replacement for MP ring. It's significantly faster and also it's correct, unlike either buffering or MP ring, which we'll get into. So CK ring is weight-free for on-queue for a single writer. It is serialized for multiple producer at the moment. There's a new data structure coming up which fixes that. It should be merged within the next 2 weeks. And then on the DQ side, it is either lock-free or weight-free fully. The other nice thing is this does play well with shared memory, so all the control structures can be allocated out of band. Another cool thing in Concurrency Kit is we have various Hashtable implementations in there that provide nonblocking progress guarantees. At the time this was developed, the state of the art as far as scalable, lock-free hash tables were concerned was kind of abysmal. Either it relied on chaining, which means you have to do memory management, or there are a lot of expensive operations on the fast path, and it places limitations as far as how collision resolution could be done. And then in open addressing, really the only work that was done here was for a hash table built on Java, so it required garbage collection, had very weird lifecycle semantics for keys. And in addition to that, it also required regular maintenance of the hash table, so particularly to clean up tombstones. So for delete heavy workloads, it was fairly abysmal. So what was done here is we ended up specializing the hash table implementation. So we don't care about termination safety. So if one thread dies in the middle of an operation, then in our case, the system is just screwed. So it wasn't a requirement for us. There was, in this particular workload, it's single writer, mini reader. So this allowed us to implement a hash table which relied on less complex instructions. The primary target was TSO, where we could leverage certain memory ordering guarantees. So what Concurrency Kit has today is there's a general technique for achieving lock-free, weight-free, single writer, mini reader, open address hash tables with zero cost on TSO and fairly minimal cost on relaxed memory ordering architectures. So at the very least, you don't have any full fences on the fast path. The cool thing about this is it applies to any open address scheme. So in Concurrency Kit, we have a variant that uses double hashing, and then we have another variant that uses Robinhood hashing if you have a workload that's a lot more delete heavy. And this is the fast path, right? So on TSO, there's basically no cost on the fast path. It's significantly faster than Google Dense Hash, 2 times as fast, if not more. And again, this is a head-to-head single-threaded benchmark. And then under a concurrent workload, it's single writer, so obviously it performs well for the writer. It is wait-free for the writer. And then for readers, depending on your write workload, it is lock-free. But if you have a good amount of fairly uniform distribution there, then it's practically wait-free for readers as well. So there's a bunch of stuff there. So I covered a lot of material. Feel free to grab me if you want to sort of deep dive into any of these topics. I'd appreciate any feedback. Feel free to follow me. Here's a bunch of resources which folks could find interesting. So if you want, we have Backtrace is my employer, so there's Backtrace. We do have a lot of interesting material on our blog regarding concurrency and performance, Concurrency Kit, and a bunch of other open source libraries. So as I mentioned, over the next 2 weeks, we'll be merging in a lock-free bounded FIFO, which has very strong forward progress guarantees for both for any number of readers and any number of writers. Yeah, that's about it. Thank you.